So, today we will start with a new topic called Clarke and Park transformation. Now, Clarke and Park transformation is topic that is not only covered in power electronics, but it is also covered extensively in the analysis of electrical machines and drives. So, they are used equally both in power electronics as well as in machine drives. So, whatever we are studying here, so we can actually expand this concept which we are going to deliver today. So, this concept is very important and one of the fundamental subjects in machines, power electronics, drives, etc. So, basically Clarke and Park transformation is a mathematical tool, it is a mathematical concept. Of course, it has some physical significance and there is also a visualization, but it is basically a mathematical treatment of the variables, for example, voltages, currents, and these are very useful. This mathematical treatment is very useful for controller design. Okay. And so, this concept we will use in future for controller development. Okay. So, let us go through this topic and slowly we will understand what is the significance and why do we do this transformation. So, basically the content is Clarke and Park transformation, which we will deal in the next few slides. So, we will start with the space vectors. Okay. We have covered it before, but I would like to cover it once more, and so that we have the continuity for this transformation. So, we have seen earlier that the resultant space vector for load phase voltage or current, or in fact I can say any variable, any electrical variable, they are defined as, when you have of course a 3-phase variable. So, it is defined as something which is shown in the screen, and like this V A B C T is 2/3 V A T plus V B T e to the power j 2 pi by 3 plus V C T e to the power j 4 pi by 3. So, here earlier in the course we had defined this variable as something V R T, V resultant T, but now we are defining in a slightly different notation, where we are defining V A B C T as a bold letter. First of all, it is bold letter because it is a vector, that is why we have put it a bold symbol. We have a time variant here. So, that means this is a time varying vector. Okay. The magnitude and the position is actually varying, and there is this A B C at the bottom. Okay. What does this A B C at the bottom of this variable indicate? It indicates that this variable is defined in the ABC reference frame or in the ABC reference axis. What is this reference frame is something which we will discuss today, and it will become slowly clear to you. But we observe that because we are using quantities like VAT, VBT, VCT here, which are time varying quantities in the A phase, B phase and C phase. Okay. So, therefore, we have used this ABC as the subscript in the notation of the space vector. So, similarly, if you see IABC is a bold letter with a time varying notation, and there is this ABC at the bottom, and ABC means that this space vector is defined in the ABC reference frame, which roughly translates to the fact that there are quantities IA, IB, IC with which we are dealing with. Okay. So, here you can see this is IAT, IBT and ICT. Okay. So, what does, so there is of course a 2/3 also at the beginning, but what does this mean physically? If you want to visualize it, what does it mean? It means that there are 3 stationary axes, and these stationary axes are the A axis, okay, then there is a B axis and then there is a C axis. Okay. There are 3 quantities IAT, IBT and ICT. These 3 quantities are on this axis and they are oscillating. So, IAT, this is like oscillating here, IBT is oscillating on this axis and ICT is oscillating on this axis. They are oscillating. Okay. And the resultant vector, which is suppose here, this is the VABC resultant, this is bold. Okay. This is the vector VABC. This is a combination of the total combination of these 3 IA, IB, IC, T. Okay. And this equation tells us how VABC is related to VAT, VBT and VCT. So, there are 3 quantities VA, VB, VC, which are instantaneously they are varying with respect to time on 3 axes, A axis, B axis and C axis, and the resultant is the VABC. If they are perfectly balanced, they have equal amplitudes and moving at the same speed, then we have this space vector rotating at a particular speed, which is equal to the speed at which, or which is equal to the frequency at which these VA, VB, VC are oscillating. Okay. And the VABC vector has a fixed magnitude when the system is balanced. When the system is unbalanced, then the VABC vector may not actually track a circular path. I mean, this VABC may not have a circular trajectory. So, if VA, VB, VC are unbalanced, then, so if they are balanced, then it is tracking a circular path. Okay. However, if they are unbalanced, then this VABC may track a elliptical path like this. Okay, unbalanced case. It may be an elliptical thing. In fact, we will see here that in that case, when it is unbalanced, in a more general case of unbalance, it is actually a 3-dimensional plane in which VABC vector will rotate. I will come to that 3-dimensional plane, but we see that in case of a balanced system, this VABC or IABC, whatever you say, both are equally valid. So, VABC is tracing a circular path, and in case of an unbalanced system, it may trace an elliptical path. Okay. So, suppose let us take an example with actual values. So, you have here this IABCT, which is defined as per definition of space vector, is this thing what is shown in equation 1. So, if suppose IAT is Im cos omega t, IBT is Im cos omega t minus 2 pi by 3, and ICT is Im cos omega t minus 4 pi by 3. So, it is a perfectly balanced system. So, when you put these values into equation 1 and substitute the values of e to the power j 2 pi by 3 as cos 2 pi by 3 plus j sin 2 pi by 3, then you see that IABC t here is equal to Im e to the power j omega t. Okay. And of course, this shows that the resultant current space vector, that is IABC t, has a magnitude or an amplitude which is same as that of the peak of the current Im. It has an amplitude, this is the amplitude Im, same as that of IAT, IBT and ICT, and it rotates at the same speed. So, here you see e to the power j omega t indicates that IABC, that space vector, resultant space vector, is rotating at omega speed, which is same as this omega here. Okay. And we have used this 2/3 factor in the space vector definition, and that 2/3 makes it magnitude invariant. What is magnitude invariant? Means that the magnitude of the space vector, that is this Im, the magnitude of the space vector is same as the peak of this current here. Okay. That is why we have used a 2/3 factor. Fine. Now, how do you see it graphically? We have covered it earlier also, but let me repeat it once more. So, the equation that I had shown earlier represents these 3 waveforms with respect to time. So, here is your omega t, and here is this Ia and Ib and Ic, 3 waveforms denoted earlier by the 3 equations. So, then at omega t equal to 0, okay, I can find out what is the magnitude and the position of the space vector. So, the peak of the current is 1 in A phase. So, as I told you, there are 3 axes here, and these 3 axes are, let me draw it with a different color. So, there is this A axis here, and on then there is a B axis here, and then there is a C axis here. These 3 axes are stationary, they do not move, they are not moving, the 3 fixed stationary axes, and on this the currents are oscillating. So, Ia, so for example, at omega t equal to 0 at this condition, Ia is oscillating, and at omega t equal to 0, that means here Ia is having its peak value and Ib and Ic are having a negative minus half value. right. So, therefore, I A must be at 1 and on this maximum length, whereas I B is minus half, and so this is the minus half, but on the negative of the B axis, and I C is also minus half. So, its magnitude is, so this one is half minus half and on the negative of the C axis. So, when you do a vectorial addition of these three quantities I A, I B, I C and multiply by 2 by 3, then you will see that the resultant I R here is having the same position as I A and its amplitude is same as the peak value of I A, which is 1 in this case. We had just seen mathematically I M, it has the same I M. Now, let us take a second case. Let us take what happens at pi by 3. So, omega t equal to pi by 3, and there we see that I A has a positive value, but it has decreased from 1 and is equal to half. Okay. I B has gone from minus half to plus half, whereas I C has gone to minus 1 at omega t equal to pi by 3. So, let us put these values on A axis, B axis and C axis. So, I A is equal to half positive, I B is equal to half positive, and I C is equal to minus 1. So, I C is 1, but at a negative. Again, if I do a vector addition of these three quantities, I see that the resultant vector is here. Okay. And similarly, you can therefore go on doing the same analysis at different time instants, and you can therefore understand that visually also or graphically we can see that the space vector is rotating in this plane. Okay. I A, I B, I C, the space vector is rotating in the plane at a speed equal to omega, which is again same as the frequency in which I A, I B, I C are oscillating. Okay. Let us see it a little bit in a slightly different way. So, the resultant space current space vector is rotating in the plane in which I A, I B, I C are oscillating. So, of course, it must have a real part and an imaginary part. Here you can see that as the vector I R is rotating, see here I R is going on rotating. So, therefore, as it is rotating, it must have a real component and an imaginary component. So, the I R is rotating. So, this is the I R space vector. So, it is rotating on the plane of this paper. Okay. The paper on which I am, or the screen on which I am drawing this vector, space vector, in this plane the IRT vector is rotating, and of course, it will have a real component and an imaginary component. So, what is the real component? The real component, if I substitute there was an with IBT there was e to the power j 2 pi by 3, which e to the power j 2 pi by 3, which I can expand and can write as cos 2 pi by 3 plus j sin 2 pi by 3. With ICT, I had a e to the power j 4 pi by 3, which I can expand and write it like this, cos 4 pi by 3 plus j sin 4 pi by 3, right. So, if you expand it and take the real component and the imaginary component. So, this is what I have done, real part of IABC and imaginary part of IABC. What do I get? I get this quantities 2/3 IAT minus half IBT minus half ICT and imaginary part as 1 by root 3 times IBT minus ICT. Okay. So, this is the real part and the imaginary part, and these real and imaginary parts again they are. So, as IRT is rotating, so IRT is rotating, so the projection, so this is the projection on the x axis and y axis, this is changing with time, right. So, as IRT is rotating, the projection on the x and y axis will go on changing. In fact, the projection on the x axis and the y axis will vary sinusoidally. So, if you are standing, if you are an observer who is standing on the x axis, you will see that this, as the vector is rotating, you will see that the projection here is oscillating. Similarly, if you are an observer here, stationary observer, you are standing on this axis and observing the projection of the rotating vector on that axis, then you will see that there is a oscillation happening. Okay. Now, in Clarke and Park transformation, we give this projection on the x and y axis the name I alpha t and I beta t. So, which means that now we will not write it at x and y axis, rather we will write it as alpha axis and beta axis. Okay. So, these are two stationary axes, okay. They are not moving, they are stationary axis, they are displaced by 90 degree from each other, and there are two observers, stationary observers on these two axes alpha and beta, and they are observing how the projection of the space vector is on that particular axis. Okay. And so, the projection is given as this I alpha t, I beta t, they are time varying. So, that is why the t, you have to note, it is a t and it is a projection. So, here you can see that this is a vector. So, it is a bold, this one is vector, it is bold. However, these are instantaneous quantities I alpha t and I beta t, these are instantaneous quantities indicating that it is the projection of this vector on the alpha axis and on this beta axis. Okay. Now, for a general unbalanced system, so far we have been saying that it is all a balanced case. Now, suppose there is a generalized unbalanced case, okay, where it is a 3-phase 4-wire system and the sum of the 3 currents IA, IB, IC is not equal to 0. So, there is a neutral current present. So, in that case, this IA plus IB plus IC is not equal to 0, and so we define something called as I0, and then we, how do we define it? We define it as the sum of the 3 currents divided by 3. Okay. So, this is by definition. I 0 t is 1/3 of I A t plus I B t plus I C t. In case of voltage, we can also define in a similar way V 0 t as 1/3 of V A t plus V B t plus V C t, and sometimes we tell or we say that this voltage is a zero sequence voltage or a common mode voltage. Okay, we have seen this common mode voltage earlier in our discussions. So, this V 0 t is like 1/3 of V A t plus V B t plus V C t. It is present at the same time in equally on the three phases. So, now we define this new vector I alpha beta 0 t. Okay. Now, it is not a it is incorrect to say it is a new vector, it is not a new vector, it is the same space vector, but now we are observing from the alpha beta 0 plane, or we are seeing it from the alpha beta 0 reference frame. Okay. Or I should say that we are observing the same vector I, the space vector, from the alpha beta 0 plane. Okay. I will talk about this alpha beta 0 plane in a few minutes. Okay. But now you see the space vector, earlier I was defining the space vector as something like this with bold, this is all bold. So, I was looking the space vector from ABC axis. So, that is why I use the notation of I ABC t. Now, I am using I alpha beta 0 t to represent the same space vector, but now observing from the alpha beta 0 plane or alpha beta 0 dimensions. So, what is this I alpha beta 0? It has this I alpha, I beta and I 0. What is this I alpha, I beta and I 0? We have just now in the previous slide, we have found I alpha t as this one, I beta t as this one, and I 0 is this one. Okay. So, I can write it in a matrix form. This is a much more compact form, where I write I alpha as I have substituted this value. So, I A times minus half I B plus minus of half I C times 2 by 3 at the outside of the matrix. Okay. Similarly, I beta I can write as 0 root 3 by 2 minus root 3 by 2. So, it is basically root 3 by 2 I B minus I C times 2 by 3, and of course, 1/3 I A I B I C. Okay. So, this matrix is called the, so this matrix is basically transforming an ABC variable into an alpha beta 0 variable, and this matrix is called the Clarke's transformation matrix, which we see T C. Okay. T C. So, T C is this matrix here. Okay. Clarke's transformation matrix. This is equal to T C. T Clarke. So, I have used T C here. Okay. So, T C transforms any ABC variable into alpha beta 0 variable, which means that a space vector observed from the ABC reference frame or from the ABC plane is transformed to a space vector observed in the alpha from the alpha beta 0 plane. Okay. So, this is what the Clarke's transformation matrix does. So, I can write it here I alpha beta 0 I is equal to T C times I ABC T. Of course, you can do the inverse of it. So, you can say I A B C T is equal to T C inverse I alpha beta 0 T. So, if you substitute and do the inverse yourself, you will find out that T C inverse is this matrix here. Okay. So, with these two matrix T C and T C inverse, you can transform any space vector from A B C to alpha beta 0 plane or alpha beta 0 to A B C plane. Okay. So, this is the matrix which connects them.